Good day, everyone. Welcome to day 2 of our Ansys online session. In today's class, we are going to be talking about static structural analysis using Ansys Workbench and Ansys Mechanica. So the first step we are going to do is to open up our Ansys Workbench software. Okay, so and the next thing we'll do is to drag and drop a static structural analysis from the analysis system into the project schematic. So I'll drag and drop into and create a standalone static structural analysis. Okay, the next step is to add our geometry, that's our model. So I will right click on the geometry tab and scroll down to import geometry and import our model. Okay, click on browse to open up our file explorer. I'll select the beam structure. Now click open. Okay, the next step is to double click on the model or right click on it and then click on edit to open up our Ansys mechanical interface. Okay, so our Ansys mechanical interface is now open and our model has been loaded. So this is a beam structure. This is a wide flange beam structure. So we are going to carry out a static structural analysis on this beam structure. So the first thing we'll do, currently we are going to, when you go over to your project schematic at the left hand side of our software or our screen rather. Under the geometry tab, you can see we have the good check mark telling us that our geometry has been inserted. Then the next step is your material, to assign your material. By default, Ansys have assigned the structural steel material. So we are going to use the default material in this case, which is structural steel. Okay. So the next thing is to mesh our model. Okay, so we have for 3D objects. If you want to carry out a 3D meshing, we have two types, either the tetra the tetra mesh element type or the hex mesh type. Okay, so how do you switch in between both of them? So I will right click on my mesh and go to insert. Then under insert, I'm going to insert method. Okay, by default it is set to automatic method. So I want to assign a I'm going to assign this this model, our beam structure, to this automatic method. So how do I do that? I'll go to my selection tab here and make sure it is set to body selection. So currently it's set to body. So when you hover around it or you try to click in between, you can see this one is edge, this is face, and this is body. So I'll select the body, select this body, and then apply. Okay. Then the next thing is under method, currently set to automatic, but I don't want that. I'm going to change that to tetrahedrons, meaning that it will create a tetra mesh for this body. So I'll select tetrahedron, okay, and I'll now right click and generate mesh. Now wait for our mesh to generate. Okay, so our mesh has been generated for this model. Okay, but we don't want this. So we want a more refined mesh for our analysis because, like I said in our first class, that your mesh refinement determine the accuracy of your results. Okay, so I will left click on my mesh and scroll down to details. Under element size, details on mesh. Under element size, I will change the element size to 10 millimeter and I will click enter. Then you can hover around this to view the size of a 10 millimeter mesh element size indicated by this circle on the screen. Okay, this circle close to the cursor on the screen. So that will tell you how wide the element size is relative to your CAD geometry. Okay, but this is also too big. I'm going to reduce that to 5 millimeter. So I'll click again, impute 5 millimeter and press enter. Okay, we'll try to compare this. Okay, this will give us a better result. This is smaller and better relative, has a better element size relative to our CAD geometry. All right, so I will right click and regenerate that mesh. So wait for it to generate. Currently it's at 5%. So wait for it to generate a more refined mesh for us. Okay, it's going to generate. Okay, now we have a better refined mesh here. All right, so we have a better refined mesh. So this is a tetra mesh. So we also have the second option, which is a hex mesh, but we can do that later. Okay, so we are going to do the first analysis using this tetra mesh and using the hex mesh and try to compare the results. So the next thing we'll do is to apply our boundary condition. So we'll scroll down to the static structural, right click on it, and then insert a fixed support. I'm going to apply a fixed support. I'm going to apply a fixed support to both edge, to the face of both end, the end of both beam. Sorry, the end of the beam, both end of the beam. So I'm going to use I'm no longer going to use. Okay, so I'm no longer going to use body selection in this instance now. I'm going to use face selection because I'm trying to fix both end of this beam structure. So currently it is set as face selection, but if it's not, you can always choose it. You can always interchange between them to select the one you want. Okay, so since it's currently set as face selection, I'm going to select this face and hold down my control and select the second face. Okay, now click on apply. Okay, you can see in our fixed support we have two faces selected, which are this face, and this face. Okay, so I'm going to apply. The next thing we're going to do is to apply a force on the top of the beam structure. So we go to your static structural on this project schematic, right click on that, and then go to insert. Then under insert, I'm going to scroll to force and select force. I'm going to select the face of this top face of our beam structure. I will select it and then apply. Okay, so our that face has been selected. So go down to magnitude. There we're going to apply. There is asking us what's the amount of force we want to apply on that surface. So I'm going to say 1000 newton, 1000 newton, and press enter. So the next thing is to confirm. I'm going to hide these tabs. Okay, so the next thing is to confirm. Currently, our the force is pointing upwards, so which is not what we want. We want the force to point downwards towards the face of this beam structure. So I'll go to my direction just below the magnitude section. I'll click on direction and I'll use this arrow here to change the direction. So currently it's facing up, so I'm going to click on the next arrow to change the direction. Make sure it's facing down, then I'll click on apply. Okay, so now the direction of our force has changed to the appropriate direction. So currently it's facing downward, which is what we want for this analysis. So the next thing we'll do is under the solutions tab, we are going to right click on the solution and then insert our stress value. So as insert stress, in this case we want the equivalence stress. So we've added every necessary boundary condition. So we are going to solve. Then after solving, we are going to carry out another analysis with the same boundary condition, but the next one we are going to change the mesh type to hex mesh and compare both results. Okay, so I will right click on the solutions and then click on solve and wait for it to solve. Okay, currently it's at 10%. So depending on the quality of your mesh or the more number of your or the number of your nodes and elements, if you have more number of nodes and elements, the analysis will take more time to solve. Okay, so our result is almost complete. Okay, so our analysis have solved. So the next thing we'll do is to view the result. So I will go to equivalent stress, left click on it to view the result of the stress. Okay, you can even simulate that on your graph section. So if I could click on this, okay, you can see how it deforms, how the stress causes a deformation on the beam structure. Okay, okay. So the maximum stress in this analysis using our tetra mesh type, we got a 5.6 megapascal. Okay, maximum stress 5.6113 megapascal. So we are going to carry out another an analysis, but in the next one we are going to use a hex mesh right instead of a tetra mesh and try to compare the values. Okay, so you can also scroll down to the um, under the mesh tab, go down to the statistics and open up to see the number of nodes and elements in this particular mesh body. So currently we have 6,000 elements and 14,000 nodes. So we are going to compare that with that of the hex mesh. So you go to your mesh and right click and scroll down to clear generated data. So I'm going to see it will tell you to, do you want to clear your all the meshes and results from any do you want to clear all meshes results and any restart points from this model? We say yes to clear our mesh data. Okay, so I'll click on this and delete it. So the next thing I'm going to do is to insert a method. Okay, in this case now assign our body. Okay, then change the method to hex dominance, telling the software that you are trying to create, you want to create only hex meshes. But in some cases, depending on the nature of the model or the geometry, the complexity of the geometry, software might not be able to generate to create a perfect hex mesh for you. It might create a good number of hex mesh and then add some tetra mesh to it. But we are going to select the hex dominant and then regenerate our mesh. Okay, currently it's at 5%. You wait for it to regenerate. Remember what I told you, your mesh refinement determines the accuracy of your result and how long it takes for your results to solve. Okay, so more mesh data means that it will take more time for it to solve. Okay, and generally hex meshes produce better results than tetra meshes, but they are difficult to produce throughout a complex geometry. That's why we normally use tetra meshes for our result. But here we have a perfect hex mesh. As you can see, all meshes here are hex mesh. So we'll go scroll down to the elements and nodes section. Under nodes, we have 21,000, which is closer to what we had in the tetra mesh. Then under elements, we have lesser elements here. We have 3,000 here, which is lesser than what we have in the tetra mesh. So our result will solve faster than the tetra mesh type. Okay. So although the difference is not much, the difference in node and element is not much, but at least there is a little. I will say it's less than the tetra meshes, although by a little percentage. So we'll go to the solutions tab and try to resolve and try to and click on solve and compare the results of our stress values. In the tetra mesh, we had 5.6113 megapascal. So we are going to compare it with this hex mesh. Remember I told you that generally hex mesh produce better results, but due to their difficulty in generating them, it's much more difficult to generate depending on the complexity of the model. So due to that difficulty, we normally go with tetra meshes for complex geometries. So our result is done solving. So our result has is we our result have been generated So click on equivalent stress to view the stress value. Now you can see from the stress result, we have 6.2874 megapascal as the maximum stress. Okay, so with our hex dominant or hex mesh method, we were able to generate better results, better stress results. Okay, so in this case, we have 6.28 as compared to the 5.6 something that we generated in the tetra mesh. So this gives you a better result than that of the tetra mesh. Okay, so you can view the point of maximum stress and minimum stress by using the probe button, maximum, and click on minimum. It will show you this is the point of minimum stress and this is the point of maximum stress. Okay, you can use your zoom box zoom to zoom that area for, sorry, zoom that area. So this is the point of maximum stress. Okay, so you can try also do that for minimum too. So this is the point of minimum stress. Okay, so we can try and refine the mesh here, mesh data here. Okay, before I will conclude the class, I would like to point out that under the mesh method, if I should click on insert under the mesh method, when I switch over to the tetra meshes, we have two types, which is under the algorithm, you have the patch conforming method and the patch independent method. They are both tetra meshes. The only difference is that in patch conforming method, the software generates the mesh on the surface and try to mesh it through the volume. So the mesh generation starts from the surface and then proceed into the volume. But in the patch independent method, the mesh is generated in the volume and is transferred to the surface. So you will have more better mesh refinement inside your model than on the surface for patch independence. But for patch conforming method, you have better mesh refinement or mesh generation on the surface than inside the body. So that's the difference between patch conforming and patch independent. So this is how you carry out a static structural analysis on any geometry you want to do. Okay, so thank you very much, and that concludes today's session. So see you in the next class.